So far, we have only considered the case of a constant force. Now let us consider the situation where the magnitude of the force changes as the crate moves. The direction of the force remains constant. Let us go back to our crate being pulled along a horizontal surface by a horizontal force F. The force is directed along the x-axis, and the magnitude of F is now a function of position along the x-axis. In other words, F is some function f of x. Note that the magnitude of F changes with the position of the crate, but doesn't change over time. This diagram shows a plot of such a one-dimensional variable force, showing how the magnitude changes as a function of position x. So how do we determine the work done by F in moving from position x1 to position x2? We divide up the total displacement into a large number of small equal intervals delta x. Consider the small displacement delta x from x1 to x1 plus delta x. During this small displacement, the force F can be considered as nearly constant, and so the work done during the small displacement delta x is given by delta W1 equal to F1 delta x, where F1 is the value of the force at x1. The work done during the next small displacement is given by delta W2, which is equal to F2 times delta x. So the total work done by the force F as the crate moves from x1 to x2 is given by the sum of all the incremental work done, sum of delta W, as shown here. So that is just equal to the sum of Fi times delta x. As the number of intervals becomes very large and their size very small, this becomes in the limit W is equal to the limit of delta x tending to naught of the sum of Fi delta x, which is equal to the integral from x1 to x2 of f of x dx. If we know the function fx, we can substitute it into this integral to find the total work done. Notice also that the work done is equal to the area between the fx curve and the x-axis between the limits of x1 and x2. Okay.